In this video, we're going to consider what happens to a dipole when it's placed in an external electric field. Many materials, glass and others, their atoms and their charge distribution when they place in an electric field get distorted, creating what's called a permanent dipole moment. To understand how those materials interact inside electric fields, we need to take a look at the model of the dipole. In this thing, I have a small arrow that represents the dipole pointing here along the x-axis. You see that it doesn't show the actual atoms because, for instance, in the atomic case, these distribution between where the electron would normally be and its distortion with the proton is extremely small compared, for instance, to the size of a pane of glass. So generally it's thought to be almost a point. However, to actually analyze the material, we're going to actually show our model of the plus q and minus q, where this distance d, which might be on the order of, say, a nanometer or even angstroms, has been expanded so that we can see it. An electric field is placed externally and it's at some angle, let's say theta, with respect to the direction that our dipole is. Now, here I've shown the electric field again, and I put a minus and a plus to indicate, well, this is the electric field at the location of the negative charge, and this is the positive charge, and that these might be slightly different. However, in general, we're going to find out that they're so close together that the electric field is the same. How do we find the total force on the dipole? Well, we just apply our definition that the force is the electric field times the charge, and then we use superposition to sum up those forces. So the total force F is equal to the force on the negative charge and the force on the positive charge. So the force on the dipole is in fact minus Q times whatever this electric field is at the negative charge's location, plus Q times the electric field at the positive charge's location. We can factor out a Q, and we get it's the difference between the electric field at the positive charge's location and the electric field at the negative charge's location. But assuming electric field is constant over the size of the dipole, which is usually true for many materials, then E minus equals E plus, and you could just call that in fact E. And in this condition, if E minus is equal to E plus, then this whole term here is 0. And so F equals 0 for the dipole. In an external electric field. That means that the electric field does not try to accelerate translationally the dipole. The glasses, for instance, or anything containing the dipole is not going to have those atoms try to move across, and because they bang into it, cause a whole sheet of glass or something else to fly across the room, accelerating. It doesn't do that. That's not what they try to do, whether in a liquid or a solid. But what can happen, we're going to find, is that there can be torques causing them to want to rotate. And so that will be our next video.